Let's take a look at using the conservation of energy to figure out how fast the Viper is moving at any point along its path during the ride. First, let's start off with a simple sketch. The coaster starts at point A and falls to point B. At point A, it has a very high potential energy and relatively low kinetic energy, not moving as fast. And then as it falls, it transforms its potential energy into a high amount of kinetic energy at point B with a relatively low amount of kinetic potential energy since it's at a lower point. Let's go ahead and list off the knowns and unknown information. In this problem, let's say that at the very start of the ride, the initial velocity is 2.1 meters per second. It's not moving very fast. It's at a height of 120 meters, and the mass of the cart is 2,500 kilograms, along with the passengers. At point B, let's say the height of the hill is only 60 meters. The mass is still 2,500 kilograms, and we want to know what's the final velocity at point B in terms of the speed of the ride. The big idea here, in terms of relating our knowns and unknowns, is to use a simple concept, which in equation form we can express as the energy initial should be equal to the energy final for any system. In other words, the energy is conserved. Expanding on this, we can say that the KE initial plus potential energy initial should be equal to the KE final plus potential energy final. In other words, the energy at point A should be equal to the energy at point B, which is in the form of kinetic plus potential. If we expand for KE and PE by substituting in the statement 1/2 mv squared for kinetic energy and mgh for potential energy, we get something that looks like this. It looks complicated, but it's not. It simply states that the initial energy at A is equal to 1/2 mass times velocity initial squared plus its potential energy, which is equal to mass times gravity times height initial, and that'll be equal to the energy at point B, which is equal to 1/2 mass times final velocity squared plus its potential energy, which is equal to mass times gravity times height final. This looks really nasty. It's actually not that bad if you just remember the big idea that the initial energy is equal to the final energy for any system, and in terms of a roller coaster at any point along its path. Let's go ahead and shove in all the numbers in terms of our knowns and unknowns. And the statement gets really big and ugly. But all we're doing is just putting in what we know for mass, initial height, initial velocity, final height, and mass. And you can see that we have our single unknown final velocity right here. This is what we're trying to solve for. Okay, let's go ahead and punch these numbers into our calculator and simplify and see what we get. We can solve for the initial kinetic energy by multiplying through 1/2 times 2,500 times 2.1 squared, giving us 5,512.5 joules. Do likewise for potential energy, giving us 2,940,000 joules. And on this side, we can only solve for the potential energy because we know the height and we don't know the final velocity. That's the whole point in this problem. Let's go ahead and solve for the left side by adding up the potential and kinetic energy, yielding 2,945,512.5 joules. That's the total energy that's in the system at point A, and that's what we'll end up with at point B. At point B, though, we know that we have 1,470,000 joules of final potential energy. So we can subtract this from both sides in order to figure out how much kinetic energy is left over at point B. Subtracting 1,470,000 from both sides yields 1,475,512.5 joules. That's equal to 1/2 2,500 times final velocity squared. Half of 2,500 is 1,250. Divide both sides by 1,250. Gives us 1,180.41, which is equal to the final velocity squared. So how do we solve for final velocity squared? Just take the square root of both sides, giving us a final answer of 34.4 meters per second. And this number here is very reasonable. 34.4 meters per second. If we multiply by 2.24 meters per second for every mile per hour, is roughly a little bit over 70 miles an hour. which is very reasonable in terms of the ride. And there you have it. So to recap, we made a little sketch of the energy transformation. We wrote a conservation of energy statement. We expanded it for both the initial and final sides. We substituted in the equation for kinetic and potential energy. We stuck in all the numbers, and then bingo, we got to our final answer. And pretty much, in terms of the technique, this is how you'll solve for any of the unknowns of a ride for any point by using conservation of energy. And there you have it. Good luck, and have fun as you explore the physics of roller coasters.